Great. How's everybody doing? Yeah? So I'm the last talk, so that means I can go over. Maybe a little bit. Let me just...
I like it.
Yeah, thank you. Yeah. So a little bit about me. I was stationed here. I was in what was called 1st Radio Battalion back in the 90s. I'm that old, yes. And it was an amazing experience. In fact, 1st Radio Battalion is now in California, so I'm glad I had that opportunity while it lasted. I really enjoyed Waimanalo Beach, and I think I spent too much time at Duke's and Moose's and World Cafe and Zanzibar and Pier Bar and... Yeah, these are old places, right? All right, so it's been 8 years since I've been back to Oahu, so I was wondering if there are any new transportation options. So I Ubered. It was a long trip. I actually did confirm and did try to pay, and I canceled at the last minute because it was an unknown amount, and I was like, this could be bad. So after the Marines, I went to the University of Florida, and I later worked for government contractors such as PwC, Booz Allen, and then I went into commercial world with Leviathan Security. Now I'm at Okta. Who here has heard of Okta? A couple of you? Okay, so we do identity access management, and I'm the lead researcher on the internal research and exploitation team, or otherwise known as REX. A nice little dinosaur. I also write code, and I like to flip bits for fun. That's my GitHub. No SIGINT work in that background at all, with Secret Squirrel being the name, right? I wrote something called Backdoor Factory, which will do file infection on ELF, Mako, and PE files, and the files still work normally. It does it on the fly, it's automatic, it does it statically. I wrote this in 2013, and then I wrote BDF Proxy, which will infect binaries during download over HTTP. It's kind of fun. So this led to me finding a cybercrime group infecting Windows applications over Tor, and this was back in like October 2014. Yeah. So enough about me. Today we're going to talk about some code signing basics. I'm going to give you a demo. I'm flipping the script. I'm going to do the demo up front to show you impact. Then I'll talk about the details and do some whataboutisms with Gatekeeper. And then we'll talk about the disclosure process, how to do these things correctly, and how I found the vulnerability. So code signing is a security construct that allows for consumer end users to verify who signed the code, and also to verify that the code in question has not been modified. Any failure, either at the OS level or in third-party developed tools, can have disastrous side effects, especially for security practitioners that do defense and incident response. Now, both Windows and macOS support the concept of portable signed code. There have been issues in code signing in the past. However, we're focusing on issues in macOS third-party developed code. So I'm going to go ahead and do the demo. Excuse me while I try to fix everything here. Okay, in this demo, we have Google Santa in full lockdown mode, and Google Santa is a whitelisting tool. Who knows what whitelisting is? A lot of you? Okay. So this is developed by Google, and they use it internally. By default, only native Apple code and macOS App Store code can run. And in this demo, the concept is that I was able to get onto the box via phishing, social engineering, such as USB devices, or post-exploitation. And I dropped a executable on the machine, and I'm going to bypass whitelisting. And this also will show that this can allow for persistence in plain sight. So let's go ahead and do the demo. So everybody see that? It's kind of small. So on the left we have, there's two VMs here, or two, there's a VM on the left, and in this VM it is High Sierra fully patched. There's two terminals open. The top one is a root shell, I'm going to show you a privilege escalation bug in Homebrew if you install it default. And then also in the lower terminal is just the regular admin user. And so on the right, we just have netcat listening on a port, and I'm going to get some shells back. So I'm going to open Calculator to show that regular applications run. And then I'm showing that Santa control is indeed in, or Santa's in lockdown mode. Okay. I'm going to try to execute netcat from nmap suite, and it does not execute. Santa blocked it, as it should have, because it's not signed. So I'm going to show you right here ls. So ls, this is the malicious binary, and I'm going to execute that. And you'll notice that it's in user local bin. For root and the normal user, user local bin is what is first in the path, okay? So if an attacker gets on your machine and drops an executable into user local bin, and if you have Homebrew, that means that if any attacker that gets on your machine can write to this directory. So we're going to go ahead and execute ls, and you'll see I get a connect back shell, okay? And notice that whitelisting is installed on this machine. And I bypassed it. So there we go. Now, so we have the connection back. I am the tester user. And now I'm going to show you that the same path exists for the root user. Okay? So now I'll execute ls. And then I get a connection back for root. Yep, pretty easy. So now I'm going to disable Santa lockdown mode. And I'm going to use Objective-C's What's Your Sign tool to show that it also thinks that it's signed by Apple. Now, this is not signed by Apple. So does everybody get the impact of this bug? So now I'm going to use Apple's own code sign tool to show that this is signed by Apple. That just shows who is signed. Now I'm going to do what we call strict checking to show that it is validly signed. All right, so that's the demo. So how does this, oh, yes, thank you. Let me change the arrangement. All right. All right, so this bug was published a month ago, exactly a month ago, and it kind of hit a lot of different news outlets, hit Motherboard, Ars, Gizmodo, Washington Post. And so there's a couple conditions for this bug. It takes advantage of the FAT or universal binary format, and we'll go into that. The first Mako in the FAT file must be signed by Apple, and the second one must be I386, and it doesn't necessarily have to be signed, or it could be self-signed. And one way to way it's malicious is that basically you use a CPU type in the FAT header that is not native to that chipset, and we'll discuss this. So, and the vulnerability exists in the difference between how the Mako loader loads sign code versus how improperly used code signing APIs check sign code and is exploited via a malformed universal FAT binary, and we'll talk about that right now. So I'm just going to run, this is just a file command on bin sync, and you'll see that there are two architectures, and one is 64-bit and one is I386, and that's basically, you see the diagram below that, and that's basically what a FAT or universal binary is. It's the same program compiled for different chipsets, so that it's portable between different computers. Now, and the FAT file really became into prominence with OS X Leopard because it was PPC to Intel chipset, and I think that was like 2007. So this bug could have existed in third-party tools since 2007. And there's no signing on the FAT header or the file itself, so you can modify these and no signature checks are in place. And so also the vulnerability exists in the difference between how the Mako loader loads code versus how improperly used code signing APIs check the code. So it's a bit of a bait and switch, and I'll explain that. So so you can see this, we're using a command that actually comes with Xcode developer tools called LiPo. I'm not kidding, it's actually called LiPo. It's for working with FAT files. And you can create a FAT file just by using create. Then later on there's a thin, so you can thin a FAT file. Obviously this was written before everybody was very sensitive on the subject, but maybe they should change it. We can get a petition started. So what I'm doing here is I'm going to create this Frankenstein binary, and yeah, so this is what this will look like. This tool, the header will look like in Mako View. You can download Mako View. There's I think it's on it's one of these download stuff for free sites that are totally trustworthy. So you can see that the Python x86 64-bit code is first, and then you have netcat right after that. And if I run code sign on this, you'll see that that it says that. So I'm running on Python first, and there's no team identifier, right? And then I run on netcat next, and you'll see that the signature is ad hoc, self-signed, and there's also no team identifier. Okay, so if I want to execute the Python code, Python has this interesting bug that probably could be abused. It has to be named Python. So if you rename Python to something else, it'll look for loaded libraries that are the same name as the executable. It's kind of fun. So it has to be named Python. And so I just copied it to temp, and I execute it, and you see that Python executes. Now, how can we get netcat to execute without messing up the signatures? Well, what we need to do is set the CPU type for the first binary slice in the FAT file to an invalid type for the native operating system. So basically, I just flipped a bit. By setting the CPU type to an invalid type or a non-native type, you could set it to PowerPC or whatever. The Mako loader will skip over the validly signed Mako binary and execute the malicious non-Apple signed code. It just skips right over because it can't execute. So in this example, you see that after I made that change, netcat executes, still called Python, but netcat executes. And then you'll see if I run code sign on it, it still has the same team identifier, and it's still valid. So that's pretty awesome. So what vendors were affected? Everyone that I could get my hands on and test. Everyone that had the code signing feature as part of their feature set, product feature set. And part of each bug report, we provided 4 samples to the vendor so that they can fully test it. Let me go over these. So the first one is it's not signed. That means the malicious code is not signed, and it wasn't really malicious. I wasn't sending vendors malicious code. It was just examples. And the header is malformed. The next one is actually a PowerPC, Apple PowerPC signed binary that I took off a OS X Leopard ISO that I found. It was dusty. And the header is, so it's a non-malformed header, it's a normal header, and the malicious code is ad hoc signed. The next one is ad hoc signed, malformed header, and then I actually took the terminal application that comes with Apple, and I was able to create a malicious terminal application that came back as signed. So the first vendor is F-Secure Little Flocker, Xfence. So it came back, this is what I would call the weakest sample. It came back as signed as Apple. And so Objective-C tools, if the tool had code signing as part of the feature set, my samples would come back signed by Apple. So this is What's Your Sign, and then this is Task Explorer, but I think all the tools are affected. I think Block Block, Lulu, Knock Knock, I think they're all affected. So then we have Google Santa, it's a whitelisting tool. You can see that it comes back as whitelisted, it's okay, green's good, and then it shows the full chain as being Apple. And then Yelp OS X Collector. So OS X Collector would only return an error if there was a failure, so I had to modify the code to get everything to print zeros if everything was okay. So this shows that everything's okay. And then Carbon Black. I don't know if you can see it, but it says it's valid. And it's signed by Apple. And then Virus Total. I don't know if anybody's heard of Virus Total. That was a joke. So everything came back signed by Apple. You're getting kind of the picture here. OS Query. Maybe a couple people have heard of OS Query. And they had a pretty good fix. And then Little Snitch. So Little Snitch actually did the best. They actually would tell you, so I'm going to read it because terminal differs from the version on disk. It has no code signature, but the disk version does. This means that the running process was probably maliciously modified. It's half true. The reason they do this check is because your code can be modified at runtime. So this is a pretty good check. All they're doing is just checking the runtime executable. But if you were to go into the settings, and you'll see bottom right-hand corner, it says signed by Apple. And then you look at the certificate and it shows that it's signed by Apple. And so if all your other tools are saying that it's signed by Apple, you might think that it's a bug in Little Snitch versus everything else, or vice versa. But I think most people would run the code based on my experience. So that's the list of known vendors. I feel like I have a Rumsfeld problem of unknown knowns, or known unknowns. I can't remember how that goes. But yeah, so after this came out, there were some comments on ours, and they're like, oh, thank God for Gatekeeper. And so Gatekeeper, who knows about Gatekeeper? Everybody knows about Gatekeeper? A couple of you. So Gatekeeper is a security feature that enforces code signing and verifies downloaded applications before allowing them to run, and that's only a one-time verification. So if you modify it after the fact, Gatekeeper's not going to check or doesn't do anything. But this is how Apple sees Gatekeeper, and this is how I see Gatekeeper. There's a reason I think this, and I'm not the only one. So this is a slide from Patrick Wardle's 2016 Gatekeeper Exposed talk, and I'll talk about some of the details of why many people that do red teaming and pen testing feel this way. So if you're targeted, you'll get the picture after this. So if you follow the standard method of getting app bundles and DMGs and you download them through a browser, Gatekeeper will protect you. Gatekeeper does not look at standalone Mako binaries, and that is the executable format, right? So this is what I tend to use when I'm setting up a persistence method. I just use a Mako. There's no need to use an app bundle. If somebody's using an app bundle, they've infected the supply chain tool chain of a developer. We've seen that with macOS, or they have a signing certificate, or they're not very sophisticated. Now, if you download a zip file, a zipped application bundle, compressed application bundle via zip format, you're protected, unless you use 7-zip, and then you're not protected. If your application bundle is been compressed with 7-zip, you're not protected. If the application is tarred, you're protected. Unless they use 7-zip to uncompress it, then you're not protected. If the user uses curl or wget, you're not protected. Or if the app bundle's on USB, you're not protected. So, yeah, it's a I don't consider it a security boundary, but Apple does. So initially when I found this bug, I decided to contact Apple directly. And this started, let's see, we'll just talk about contacting them first. So I sent the initial sample to Apple where the malicious code was not signed, and I already knew what they were going to tell me, so it was kind of a setup. Because I've been down this path before on code signing issues, and product security provided a recommendation, and I turn around and provide a bypass to their recommendations. And then they provide another recommendation that doesn't solve the issue, and I respond with a workflow to solve the issue, and I hope that they'll address it, because my goal with the entire problem was for them to fix it on the back end so that developers didn't have to do anything in their code, so they'd be frictionless. However, they let me know that third-party developers were going to have to work it out, and they were going to update some documentation. So I guess you're asking, your next question, is Apple vulnerable to any of this? And I tested a number of scenarios, and they are not in a security sense. For example, I cannot access keychain from unsigned code directly without entering a password. So there's really, I haven't found any instances. Maybe there are. Maybe I just haven't looked at it fully. But this is kind of an interesting bug. So this is the system information app, and my terminal POC is there, and it comes back as signed by Apple. But I don't consider this a security bug, because I hope you're not making security decisions off the security information app. But if this was built in as a security feature into Mac, then I'll consider a security issue. But as of right now, I don't. If somebody else wants to report it, go ahead. Good luck with that. So the developers were really excited about this bug, as you can probably see. This is some of the reactions. This was very common. Yeah, God help anyone using these APIs. I like that. And somebody sent me this offline. It was great. I just leave this in the background sometimes when I'm having a bad day. So how did we go? Yeah, April 9th, I was able to tell everyone we were able to find that we knew were affected. And then at the same time, I was in contact with CMU CERT. And their recommendation was a blog post to get this information out, because of the code signing aspect. A lot of people could have developed their own internal tools to check code signing, and we just, back to the Rumsfeld question, unknown knowns, known unknowns, So on June 12th, we did the public disclosure, and yeah, so here we are. So this was Apple's documentation on June 9th. Thank you, Google Cache. This is the sec static code check validity API documentation. Sometime after June 12th, it got updated. And I'll read it out. When checking a universal binary, include the ksec cs check all architectures flag. Otherwise, the method verifies only one slice of the binary, potentially indicating success without testing all slices. Be aware that the slices of a universal binary don't have to be signed by the same signer for the test to pass. One slice might be ad hoc signed. Thank you. But the validity check doesn't know which slice you're going to run. For example, the user might be using the arch command line utility to pick a 32-bit architecture, even though a 64-bit architecture is available. In fact, that flag alone is not good enough. That is also not correct, but whatever. So how do we do it correctly? So let's say you're a non-developer, or you're just doing things via the command line. You got a bunch of bash scripts that are, helping you out. That's what everybody just uses bash scripts, I guess. So there's a couple ways you can do it. Code sign, you can use 4 Vs, you can use 2 Vs. It's about the same if you look at the source. And then you got to pass this, what was called the requirement flag. And you just pass anchor Apple. And then some app, or you can do a PID, an actual running process. And that's a pretty good check if you want to see what's going on in your current process list. Now that anchor Apple only checks for native Apple applications. Okay, so if you want to check to see if it comes from a Apple cert, a sign cert, or a Apple sign developer cert, you do anchor Apple generic, same concept. And then if you want to, if the application is failing and you want to kind of figure out why, you can use LiPo, and then you have the thin command, so you can thin out your FAT file. And then you just check the output of that. Simple, right? So on the developer side, it depends how you want to do this on what you want to see. So you're going to use the sec requirement create with string, and you're going to pass anchor Apple or anchor Apple generic, and you're going to take the output of that and pass it to sec static check code validity with all of these flags enabled, all of them. I think that's every flag maybe possible for this. And then you may have to break it out even further to see where it fails. And I think OS Query actually implemented that, so they actually strip out every architecture in the FAT file to make sure that everything is okay. So yeah, so it's a pretty simple process. As far as discovery, I've been wrestling around with FAT files or signing for a little while. I reported this issue back in 2015. This was, I think, June. It was a resource error, kind of fun. But then I did a talk at ShmooCon in 2016 called Hiding from the Investigator. You could actually, at the time, I think it was iOS 9, you could take and append like a gig of data to an iOS application, upload it to the phone via iTunes, walk around with all that data, your app works fine, and then, let's say you're crossing borders, then you could just pull the file down back through iTunes and you have your data. You're able to smuggle the data, right? So that was kind of fun, kind of a fun talk. But during that talk, I noticed that, while doing research on the talk, I noticed that if you were to put a single NOP in between Mako binaries in the padding area of the FAT file, you would get a error. It just something wrong, right? Wouldn't tell you what, it just an internal error occurred. Great. So that made me want to look more into universal binaries or FAT binaries to see, what else I could find. And so I got right on that, and almost 2 years later, I decided to look at this again. It was Christmas season, everything was slower, yeah, so I took a Perl binary, used backdoor factory to infect it, and then I think all I did was append data to the end, and you see that it fails code signing strict checking, and yeah, I uploaded it to VirusTotal and it came back as valid. And I knew at that moment that I, number one, shouldn't have uploaded it to VirusTotal, because then everybody has it. But I realized at that point that I'm kind of on the right track. So being that this was really important, I put it off until February 13th. Almost 2 months later. No, what happened is I had a kid and just life got busy. So I finally got around to it around February 13th. And so I'm back using LiPo. And I tried to put I wanted to see what I could do with a FAT file format. And so I tried to put two architectures in the same FAT binary, and I failed gloriously. It wouldn't let me do it. Now, generally, if I see something like this, like a safety feature in a program, it makes me question, well, what if I did it? What would happen? So I manually created the FAT file in a hex editor, and then it goes to execute, and it failed. So I'm like, well, that's not good. So then I started playing around, I started reading source code, and I figured out that if I could flip a bit on the CPU types, that it might execute. And then I was able to solve that problem. So then at that point, I knew that I was on to something. And it didn't take, after that, it didn't take long to actually start bypassing third-party code signing checks. And after that happened, you all saw the results of that at the start of the talk. So that is my conclusion to this talk, or at least that's how I discovered the bug. In conclusion, I really encourage people to take a look if you're into reading source code and reading C. I encourage people to take more of a look at code signing. I think that you could actually find a lot of bugs in the APIs themselves. Those that probably need to be fuzzed a little bit more. And I believe that these bugs are going to continue to happen over and over and over because it's not being fully addressed by the operating system maker. And so I think that if you have a product that you run across that does code signing checks, you should take these binaries and test it for sure. And there's the blog post. If you just search "I can be Apple," you should be able to find it. But any questions? Anything at all? No, because iOS. So iOS, it has. I forgot the. There's a syscontrol that you can use on Mac that actually enforces its OS-wide code signing checks, and if this is automatically compiled into the kernel on iOS, so it doesn't work on iOS. I forgot that. I just can't remember this syscall off the top of my head. Any other questions? All right. Well, thank you for your time. Yep.
Are Macs still safer than PCs?
Actually, I don't think so. I think PCs are better. Actually, the mitigation. I did a talk on EMET last summer at DEF CON, and I was bypassing EMET, and then they fixed it, and then I bypassed their fixes. And Windows 10 is blown Mac out of the water as far as security mitigations. They're not even the same realm anymore. Any other questions? All right. Well, thank you for your time. Thanks for Shaka Khan putting this on.